Hi Bob, I've been reviewing quantum computing papers from February 2025, and there's so much interesting research. What do you think were the key developments this month?
Hello, Alice. February 2025 was indeed a productive month. I'm seeing several important themes: advances in quantum algorithms for optimization problems, new approaches to quantum error correction, practical applications of quantum machine learning, and significant improvements in hardware-oriented techniques. There's also interesting work on quantum software engineering frameworks and quantum sensing.
I noticed several papers on optimization algorithms. I was particularly intrigued by the quantum preconditioning paper. Could you explain how this approach differs from traditional QAOA implementations?
That's a fascinating paper by DuPont et al. Traditional QAOA directly attempts to solve optimization problems, but often struggles to outperform classical methods. The quantum preconditioning approach takes a hybrid stance. Instead of solving the problem outright, it transforms the input problem into a more suitable form for a classical solver. The level of preconditioning is determined by the quantum circuit depth. What's clever is that they demonstrated that best-in-class classical heuristics like simulated annealing converge more rapidly when given quantum preconditioned input for various problems, including Sherrington-Kirkpatrick spin glasses and random 3-regular graph maximum cut problems. For some problem classes, even when accounting for preconditioning time, they achieved a practical quantum-inspired advantage.
That's really interesting. It seems like a pragmatic approach to finding quantum advantage. Speaking of optimization, I also saw a paper about improving the success probability in the LHC parity embedding using quantum walks. How does this relate to other quantum optimization techniques?
The Bennett et al. Paper addresses a key challenge in quantum optimization. The LHC, Lechner-Hauck-Zahler, parity embedding is important because it allows us to implement long-range interactions in quantum optimization problems, which are typically difficult to engineer directly in hardware. What makes their approach distinctive is the use of continuous time quantum walks, rather than traditional quantum annealing or adiabatic quantum computation, AQC. Quantum walks can avoid the exponential gap-closing problem seen in other techniques by populating excited states. Through numerical simulations on Sherrington-Kirkpatrick Ising spin glass instances, they verified the efficacy of heuristics for estimating optimal hopping rates and identified post-readout error correction techniques that improved success probability. This work complements other quantum optimization approaches like QAOA and quantum annealing, offering another tool in our quantum optimization toolkit that might be more suitable for certain problem classes.
I see how these optimization approaches are evolving. There's also significant work happening in quantum machine learning. The paper on quantum machine learning in precision medicine and drug discovery caught my attention. Do you think QML is really positioned to be a game changer in healthcare, as the title suggests?
That's a thought-provoking question, Alice. The paper by Bertel et al. Makes a strong case for QML's potential in precision medicine, but with important caveats. QML could indeed transform medicine by enabling faster, more accurate diagnostics, personalized treatments, and enhanced drug discovery processes, all areas where classical computational methods often struggle with the complexity of biological systems and vast datasets. However, the authors wisely acknowledge significant challenges, including algorithmic errors and high implementation costs. What I find particularly valuable is their emphasis on formal methods to enhance reliability and correctness of quantum computing applications in healthcare. They outline how mathematical techniques can precisely define behavior of quantum algorithms, ensure correctness under all conditions, provide mathematical proof of specified properties, and optimize resource usage. So is QML positioned to be a game changer? The potential is certainly there, but practical implementation faces substantial hurdles. The paper provides a balanced view that acknowledges both the transformative potential and the significant work still needed before QML can truly revolutionize healthcare.
That's a helpful perspective. I'm also curious about the practical applications of QML. I saw an interesting paper about particle physics data encoding for quantum machine learning called One Particle, One Qubit. How significant is this encoding approach for high-energy physics applications?
A one particle, one qubit 1P1Q paper represents a significant advancement in quantum data encoding for high-energy physics, HEP. Traditional approaches to encoding HEP data for quantum computing often require complex compression techniques that can lose important information. What makes 1P1Q novel is its directness. Each particle in a collision event is assigned to an individual qubit, enabling a natural representation without classical compression. The authors demonstrated its effectiveness through two applications: a quantum autoencoder for unsupervised anomaly detection and a variational quantum circuit for supervised classification of top quark jets. The results are quite promising. Their quantum autoencoder achieved superior performance compared to a classical autoencoder while using significantly fewer trainable parameters. Similarly, their VQC achieved competitive classification performance, approaching state-of-the-art classical models despite minimal computational complexity. Perhaps most importantly, they validated the quantum autoencoder on real experimental data from the CMS detector, establishing the robustness of quantum algorithms in practical HEP applications. This demonstrates that 1P1Q provides not just theoretical advantages, but practical ones for collider data analysis. As quantum hardware continues to improve, this encoding strategy could become increasingly valuable for processing the enormous datasets generated by particle accelerators.
That makes sense. There seems to be a lot of focus on making quantum computing more practical. I noticed a paper on Qmod, Expressive High-Level Quantum Modeling, that addresses quantum programming abstractions. How might this impact quantum software development?
The Qmod paper addresses one of the most significant bottlenecks in quantum computing today: the lack of high-level programming abstractions. Currently, most quantum software development relies on gate-level circuit descriptions, which obscures the algorithm's functional intent behind low-level implementation details. Qmod introduces a high-level quantum programming language designed to capture algorithmic intent in natural terms while delegating implementation decisions to automation. What's particularly innovative is its support for quantum numeric variables and expressions, including digital fixed-point arithmetic optimized for resource efficiency. Beyond digital encoding, it also supports phase and amplitude encoding, approaches frequently used in quantum algorithms to achieve computational advantages. The impact on quantum software development could be substantial. By providing higher-level abstractions, Qmod could significantly reduce development time, improve code readability and maintainability, and enable more people to work with quantum algorithms without needing to understand all the low-level details. This addresses the growing gap between quantum hardware advancements and programming capabilities. Just as high-level languages like Python revolutionized classical software development compared to assembly language, Qmod and similar approaches could dramatically accelerate quantum software development and make quantum computing more accessible to domain experts who aren't quantum computing specialists.
That's a compelling comparison to the evolution of classical programming languages. Speaking of practical implementations, I was intrigued by the paper on network-assisted collective operations for efficient distributed quantum computing. How significant is this for scaling quantum computing resources?
This paper by Llovo et al. Addresses a critical challenge in scaling quantum computing: how to effectively distribute quantum operations across multiple quantum processing units, QPUs. As we're seeing with classical high-performance computing, networked approaches will likely be essential for scaling quantum computing beyond the capabilities of individual devices. What makes their contribution significant is the development of protocols for distributing collective quantum operations using only local operations and classical communication, LOCC. They focus specifically on collective multi-controlled and multi-target gates in network architectures similar to those used in classical high-performance computing. The efficiency of their approach is remarkable. They estimate that the bell pair cost for a single distributed multi-controlled gate requires just one additional bell pair over the theoretically optimal calculation with pre-shared entanglement. This demonstrates better scalability compared to current proposals based on entanglement swapping through a network. They also provide practical recipes for distributing gates such as arbitrarily sized Toffoli and multi-controlled Z-gates, and even demonstrate an exact implementation of a distributed Grover's search algorithm using their protocol. The bell pair cost grows only linearly with the number of Grover iterations and partitions. This work represents an important step toward practical distributed quantum computing, which will be essential for scaling quantum resources beyond the limitations of individual quantum processors.
That's fascinating. It seems like there's also significant progress in quantum hardware optimization. I noticed 2 papers about Josephson junctions, one on tuning techniques and another on barrier variation analysis. How did his papers contribute to improving quantum hardware reliability?
You've identified 2 complementary papers addressing a critical aspect of superconducting quantum hardware. Josephson junctions are essential components in superconducting qubits, and their properties significantly impact qubit performance and reliability. The Kennedy et al. Paper on tuning Josephson junctions develops a model based on depinning theory to interpret tuning rates. They show why time-varying annealing potentials result in controlled junction tuning and how such protocols can be optimized. This is crucial because post-fabrication tuning techniques can help overcome manufacturing variations, effectively improving yield and consistency in quantum processors. Meanwhile, the second paper by Kennedy et al. With different co-authors takes a complementary approach by analyzing barrier variation in Josephson junctions. They employ Monte Carlo simulations, electrical breakdown measurements, and transmission electron microscopy to characterize junction barriers. Their findings indicate that standard deviations of 15 to 20% of total barrier thickness are compatible with experimental data. And they highlight how electrical breakdown can probe the weakest points in barriers, providing a promising feedback mechanism for barrier optimization. Together, these papers advance our understanding of both how to analyze junction quality and how to improve it through tuning. This addresses a fundamental challenge in scaling superconducting quantum computers: manufacturing Josephson junctions with consistent properties. Better understanding and control of junction properties directly translates to more reliable qubits with improved coherence times and gate fidelities.
That makes sense. There also seems to be interesting work on quantum error correction. I was particularly intrigued by the paper Discovering Highly Efficient, Low-Weight Quantum Error Correcting Codes with Reinforcement Learning. How does this approach compare to traditional methods of developing error correction codes?
The paper by He and Liu represents a significant advancement in quantum error correction code discovery. Traditional approaches to developing quantum error correcting codes often rely on algebraic constructions or exhaustive searches, which become computationally infeasible for larger codes or when optimizing for specific parameters like measurement weight. What makes their reinforcement learning (RL) approach novel is its versatility and computational efficiency. Rather than searching the entire space of possible codes, the RL framework learns to identify promising code structures through exploration and feedback. This allows it to discover new low-weight codes that substantially outperform the state-of-the-art in practically relevant parameter regimes. The results are impressive. They demonstrate savings in physical qubit overhead compared to existing results by 1 to 2 orders of magnitude for weight 6 codes. This brings the overhead into a feasible range for near-future experiments, which is crucial for practical quantum error correction. Beyond just finding better codes, their approach also provides insights into the interplay between code parameters, offering new understanding of the potential efficiency and power of practically viable coding strategies. This could guide future research in quantum error correction. Compared to traditional methods, this RL approach is more adaptable to different optimization criteria, more computationally efficient for exploring large code spaces, and better able to discover non-obvious code structures that might be missed by more structured approaches. It represents a powerful new tool in our quantum error correction toolkit.
That's fascinating. I'm also curious about the paper on qubit versus qubit, simulated performance of error correction codes in higher dimensions. Do qubits actually offer practical advantages for error correction?
That's an excellent question, Alice. The paper by Keppens et al. Addresses a fundamental question in quantum error correction. Can higher dimensional quantum systems qubits, provide advantages over traditional two-level qubits. Theoretically, qubits offer more efficient information encoding, which suggests they might require less overhead for fault-tolerant quantum computation. The authors test this hypothesis by creating and simulating quantum circuitry for small qubit error correction codes with specifically adapted decoders, then comparing their performance with qubit counterparts under different noise models. They introduce a novel error ratio metric to quantify the trade-off between logical error rates and the reduction in the number of units required when using qubits. Their findings for distance 3 codes are quite promising. The logical error rates would give fewer average computational errors for higher dimensional codes, especially when decoders are adapted to correct more hyper-edge type errors that are specific to qubit systems. The practical advantages stem from the fact that qubits can encode more information per physical unit, potentially reducing the total number of physical systems needed for error correction. However, there are important caveats. Implementing high-quality qubits is generally more challenging than qubits, and controlling higher-dimensional systems typically introduces additional complexities. This research suggests that as our ability to implement and control qubit systems improves, they could offer meaningful advantages for quantum error correction. However, these advantages must be weighed against the increased implementation challenges.
I see. It's interesting how many different approaches to quantum error correction are being explored. Moving to another topic, I noticed a paper on quantum organizational readiness levels. How does this relate to the technical papers, and why might it be important for quantum computing adoption?
The Quantum Organizational Readiness Levels paper by Teitzma et al. Addresses a critical but often overlooked aspect of quantum computing, organizational implementation. While most papers focus on technical advancements, this one recognizes that adopting quantum computing within companies isn't straightforward. Unlike classical ICT projects, quantum computing implementation is fundamentally different due to the technology's immaturity, making development and use uncertain, nonlinear, and more complex. As a potentially disruptive technology, organizations need to assess both the possible business value and their readiness for implementation. The paper presents a framework for determining an organization's readiness for implementing quantum computing, similar to how technology readiness levels, TRLs, assess technology maturity, but focused on organizational capabilities instead. This helps companies evaluate where they stand and what steps they need to take before successfully adopting quantum computing technologies. This work is important because even the most advanced quantum technologies will fail to deliver value if organizations aren't prepared to implement them effectively. The gap between quantum research and practical business implementation is substantial, and frameworks like this help bridge that gap. In the broader context of February's papers, this work complements the technical advancements by addressing the human and organizational factors that will ultimately determine whether quantum computing fulfills its promise in real-world applications.
That's a great point about the importance of organizational readiness. I also noticed a paper about security concerns in quantum computing. Swap attack, stealthy side-channel attack on multi-tenant quantum cloud system. How significant are these security risks for current quantum cloud platforms?
The swap attack paper by Li et al. Reveals concerning security vulnerabilities in multi-tenant quantum cloud platforms that should be taken very seriously. As quantum computing increasingly shifts to cloud-based access models, these findings have immediate implications. The authors trace the root cause of crosstalk effects to the swap path between qubits, demonstrating that these effects can impact quantum circuits even over long distances. What makes their work particularly significant is that they verified these attacks on real IBM quantum devices, not just in simulation. In the active attack mode, they showed that an attacker executing a single CNOT gate could perturb victim circuits running Grover's algorithm, reducing expected output accuracy by over 81% through strategic qubit placement. Even more concerning, in the passive attack mode, they achieved 100% accuracy in predicting a victim's circuit size when running Simon's algorithm, using a stealthy circuit as small as 6.25% of the victim's size. These findings challenge the existing defense strategy of maximizing topological distance between circuits. Even with such precautions, attackers can still extract sensitive information or manipulate results remotely. For current quantum cloud platforms, this represents a significant security risk that needs immediate attention. As quantum computing applications expand to include sensitive areas like finance, healthcare, and cryptography, these vulnerabilities could undermine trust in shared quantum resources. The paper highlights the urgent need for robust security measures, specifically designed for the unique characteristics of quantum hardware.
That's concerning indeed. On a different note, I noticed a paper about quantum computing applications for climate modeling. Given the computational demands of climate simulations, could quantum computing really make a difference in this field?
The paper by Schwabe et al. Provides a thoughtful analysis of how quantum computing might contribute to climate modeling. Climate projections require enormous computational resources, and even with today's supercomputers, significant uncertainties remain, particularly in representing subgrid scale processes like turbulence or convection. The authors identify several promising areas where quantum computing could potentially help. Quantum computers might accelerate climate models by solving underlying differential equations faster. Quantum machine learning could better represent subgrid scale phenomena in Earth system models, ESMs, potentially even with currently available noisy intermediate-scale quantum devices. Quantum optimization algorithms could assist in tuning the many parameters in ESMs, a currently time-consuming and challenging process, and quantum computers could aid in analyzing the massive datasets generated by climate models. However, the paper is appropriately cautious about the timeline and challenges. Current quantum devices are still limited in scale and affected by noise. The authors emphasize that strong interdisciplinary collaboration between climate scientists and quantum computing experts will be essential to overcome these hurdles. So, could quantum computing make a difference? The potential is certainly there for significant impact in the long term, particularly for improving the accuracy of climate projections by better modeling complex physical processes. But meaningful contributions to operational climate modeling will likely require more mature quantum hardware and algorithms specifically tailored to climate science applications. The paper does a good job of mapping out both the opportunities and the substantial challenges ahead.
That's a balanced perspective. Looking at all these papers together, what do you think are the most significant trends or themes emerging in quantum computing research this month?
Looking at February's papers collectively, I see several significant trends emerging. 1. Pragmatic approaches to quantum advantage. Rather than seeking pure quantum solutions, researchers are increasingly developing hybrid approaches that leverage quantum computing strengths while acknowledging its current limitations. The quantum preconditioning paper exemplifies this trend, using quantum methods to transform problems for classical solvers rather than solving them outright. 2. Machine learning for quantum optimization. Several papers demonstrate how machine learning techniques, particularly reinforcement learning, can optimize quantum systems, from discovering better error correction codes to improving quantum circuit design. 3. Hardware-software co-design. There's growing recognition that quantum advantage requires simultaneous advancement in both hardware and software. Papers on Josephson junction improvements, high-level programming languages, and hardware-specific error correction reflect this integrated approach. 4. Distributed quantum computing. As individual quantum processors remain limited in size, research on effectively distributing quantum computation across multiple processors is gaining importance, as seen in the Network-Assisted Collective Operations paper. 5. Security and practical implementation challenges. As quantum computing moves toward practical applications, papers addressing security vulnerabilities and organizational readiness indicate growing attention to real-world implementation challenges. 6. Domain-specific quantum applications. Rather than generic quantum algorithms, many papers focus on quantum solutions for specific domains like climate modeling, high-energy physics, and healthcare, suggesting a maturation of the field toward practical applications. These trends collectively suggest a field that's maturing beyond theoretical promise toward practical implementation, with researchers increasingly focusing on how quantum computing can deliver real-world value despite current hardware limitations.
Thank you, Bob. Those trends really help put the individual papers in context. I appreciate your insights on these recent developments. It's exciting to see quantum computing research progressing on so many fronts simultaneously, from hardware improvements and error correction to practical applications and implementation challenges. It seems like we're in a phase where researchers are both pushing the fundamental capabilities of quantum systems and finding clever ways to extract value from current hardware limitations.
You're welcome, Alice. You've captured it perfectly. We're in a fascinating transition period where quantum computing is simultaneously advancing at the fundamental level while researchers are getting increasingly creative about extracting practical value from imperfect systems. This dual approach, improving the technology while finding ways to use what we have now, is likely to characterize the field for the next few years. It's an exciting time to be following quantum computing research, and February 2025's papers show just how diverse and dynamic this field has become.
Absolutely. Well, this has been a really enlightening discussion. I'm particularly going to keep an eye on those pragmatic hybrid approaches and domain-specific applications. Thanks again for sharing your expertise on these papers.